my name is Seoyoung Jun and my project is Solar Tree, Bioinspired Solar Panel Design and Performance Review. Throughout the past few years, my family and I have done some traveling along the East Coast. One day I noticed that the pine trees in the background looked different depending on where the picture was taken. I found that the slash pine is the most common pine tree in Florida, loblolly pine in Virginia, and eastern white pine in Maine. I did some research and found that the shape of the pine trees are optimized to get sunlight all throughout the year. This is when I got the idea. If the pine tree's shape varied depending on the location of the tree, what would happen if all the leaves on the pine trees were solar panels? This led me to create Solar Tree. The goal for my project was to prove that the performance or power output of the solar tree depends on the shape of the tree. I will compare the performance of the solar trees to the control model and find and develop the optimal solar tree design. The novelty of the solar tree is that Solar Tree suggests 3 bio-inspired solar tree shapes named Florida, Virginia, and Maine, and the obviousness is that I built the test models or prototypes of the solar trees. There were many projects with the name Solar Tree, but commercial solar trees were mainly designed to make large shades for aesthetic purposes. There were also many academic researches, but the results mostly came from computer simulations. Researchers mainly focused on the material, the orientation of the leaves, and the geological locations. At the bottom, you can see 3 different test models of the solar trees that I created. The solar tree is designed based on the shape of the pine trees. First, I found the most common pine trees in Florida, Virginia, and Maine, and designed 3 solar tree models based off of them. The control model was created to compare the performance of the solar trees to the conventional solar panel design. The distances between the top, middle, and bottom branch groups characterize the shape of the solar trees. The solar trees have the same footprint area and height, and the solar trees have the same number of solar panels. Here you can see the technical specifications of the solar trees. The measurement device was created to measure the power output from the solar trees and control model. Here you can see the voltage current meters, battery for meters, and incandescent lights for power dissipation. Here is the wiring diagram for the device. This is a Raspberry Pi and Pi camera to take pictures of the voltage current meter for data. This is the process for automated measure. Here is the power measure panel and the image capture device with Python code to capture images every 5 minutes with a date and time stamped on the image. These are the solar trees being tested on my deck: Florida, Virginia, Maine, and the control model. When automated measure wasn't available, I manually recorded data at a parking lot on a hill so I could get data even near dawn and dusk. The solar altitude is the height of the sun. Here you can see the graph of the solar altitude starting from the spring equinox, which is March 20th. The summer solstice is June 21st, and the winter solstice is December 21st. I measured data from the summer solstice to the winter solstice, so I mirrored the data to both sides to get the power output data for the whole year. Then you can see the power outputs of the solar trees and control model by month. The area under the graph is the energy produced. You can see that as we get closer to the winter, the energy produced starts to decrease, and during the day, the control model has the most energy output. But here you can see that during dawn and dusk in the winter, the main model has the highest energy output. Here you can see the power outputs from June to December for each of the solar trees and control model. Here you can see that August has the highest power output, but the important part is that the main model generated more power than the control model during dawn and dusk in the winter. Here you can see the energy output during the year. This graph is the ratio of the power output of the optimal solar tree by the control model. The best performing solar tree performs about 95% of the control model, but in December, the best solar tree, or the main model, can perform 103% of the control model. So in total at dawn and dusk, the control model cannot generate power, especially in the winter, and therefore the main model was able to generate the most power during this time. As you can see in the picture, the control model does not get any sunlight because the sun is to the side of the solar panels, but the main model is able to generate energy even during dawn and dusk in December. In the graph, you can see that the main model generated the most energy at dawn and dusk. Throughout the year, the best performing solar tree changes depending on the month and season. You can see in this image that we can transform the solar tree models by changing the heights of the top, middle, and bottom branch groups. With this, we can change the shape of the solar trees to get the optimal performance of the solar tree. Through this graph, you can see that the optimal solar tree can create about 278 watts, which is about 95% of the control model. In conclusion, in June, the solar trees and the control model generated the most energy. In December, the main model generated more energy than the control model. From June to November, the Virginia model showed the best performance between the solar trees, except in August, where the Florida model performed the best. In total, this project suggests an opportunity to enhance the performance of solar panels at dawn and dusk during the winter, as the power output of the conventional solar panel design is very low during this time frame. The future works for this project is that I will calculate the performance of solar trees quantitatively based on the latitude of the location, solar altitude, solar panel angle, and temperature. And these are my references. Thank you for watching!